Yeah, Elmwood. Have you got Elmwood? The worksheet from yesterday. Yeah, so like this one. This one. Do you all have this? If not, then hand it to me in the next lesson. Thank you, everybody. Okay. Thank you. It's so hard. It's so hard. So last lesson, which is yesterday, we stopped at the discussion of the different hardness, okay, and strength of these three types of substances, okay. And if you want to take out like that's it, yes, okay. And then you see at the bottom we have two blanks, okay, to fill in, and that's the solubility in organic solvent and aqueous solvent. So let me explain to you what these two types of solvents are, and then we proceed with filling in the table. So first we have solubility. Write this on your notebook first, and not yet on the worksheet. Okay. So solubility in solvents. Right. So first of all, you may remember learning this equation in like form 3. What is the solution made of? Solvent and solid. Okay. So they are all words starting with letter S. Okay. So can you put down solid plus solvent forms solution. So forms a solution. So and what is a solid? Okay, so solid is something that can dissolve. So solid is something that can dissolve. And to dissolve means to break into many small pieces. Okay, so when you say salt dissolves in water, it means when you put salt into water, it like separates into many fine pieces. So that's what dissolving means. So to dissolve means to break into many small pieces. So into many small pieces. And solvent, okay, is something that can dissolve the solids. And it's usually a liquid, okay, so something that can dissolve the solid. But it's not like water is the only solid. You know, we use water a lot in everyday life. We use it in like cooking, in washing. But interestingly, water is not the only solvent available. There's also what we call organic solvent. So something that can dissolve solids. And right now, there are two types of solvents. Okay, so there are two types of solvents. So one, we call it aqueous solvent. Okay, so the term aqueous, you may remember learning this when we discussed ionic compound. Okay, ionic compound, they can only conduct electricity in aqueous and molten state. So aqueous solvent means solvent containing water. Okay, so the term aqueous comes from the word aqua, A-Q-U-A, meaning water. So this is solvent with water. And then we have something called the organic solvent. And when you look at the worksheets I gave you, you see an example of organic solvent, trichloromethane, okay? So usually organic solvents are solvents without water, but they contain carbon. So solvent without water and are carbon-based, meaning they contain carbon. So an example of aqueous solvent would be H2O. So you know H2O is water, water is a solvent. An organic solvent would be something with carbon, okay? So CHCl3 or CCl4 for that matter. So these things, you see, they have carbon in them. So this is carbon, and this is also carbon. Okay? So we have solids and solvent added together to form a solution. So when you add solid, so let's say this is a spatula. So you see in the lab, we don't call the thing that looks like a spoon. We call it a spatula. So if we add some solid into like a beaker containing some solvent, together they will form a solution. So a solution is when the solid breaks into many, many small pieces. Okay, so this whole thing we call it a solution. Okay, right. These different types of structures we mentioned, giant ionic, simple molecular, giant covalent, and giant metallic, they have different solubility in different types of solvent. Some are more soluble in aqueous solvent, some are more soluble in organic solvent. Okay, so first, let's take a look at the solubility of giant ionic structures. Okay, so that's number one. Solubility of giant ionic structures such as NaCl. Okay, so NaCl will be one such structure. So e.g. NaCl. So when we add NaCl into aqueous solvent, okay, most of them would dissolve very well. Okay, I mean most giant ionic structures, and table salt of course dissolve very well in water. That you know. So you can put down in aqueous solvent. It's soluble. Okay, so soluble in aqueous solvent, but then it is insoluble in organic solvent. So write down soluble in aqueous solvent, but insoluble in organic solvent. We can sort of explain why this is the case. Okay, so you can draw an explanation on the side. Why is it soluble in in aqueous solvent, but not in organic solvent? That's because in water, so this is water. So if you have a lot of water in here, H2O, H2O, do you remember what charge does hydrogen and oxygen carry respectively? Hydrogen would carry a positive charge, and oxygen carries a negative charge. So that's water. In this regard, we say water is a polar molecule. So you will learn more about polarity in microscopic world 2 in Form 5. So water right now is a polar molecule. So just like you know the Earth has north and south pole, molecule can also have two poles. Just that we don't call them north and south pole. We call them the delta positive N and the delta negative N. And delta means slightly. Okay, so when you say delta positive, it means it's slightly positively charged. So we have delta positive. And so this will make more sense to you later, trust me, but put this down first. Okay, so delta positive means slightly positive end of the molecule. Delta negative means it's a slightly negative end of the molecule. So when you add table salt on any giant ionic structure for that matter into water, what will happen? Remember, opposite charges attract. So when the water surrounds itself around the ionic structure, what will happen? It dissolves the ions, okay, the ionic compound, because the following happens. So can you tell me which end of water would move closer to the positive ion? Oxygen, right? Yeah. Yeah, okay, oxygen. So you have oxygen. So just draw 3 water molecules around, aligning the water this way. And then negative ion, they will have the hydrogen atom, yeah, surrounding the negative ion. So this is because the hydrogen has positive N and the oxygen has a negative N, okay, it's the negative N or has a negative charge. Right, so these are very strong attraction. So if the water molecule attracts one another really strongly, okay, so you see these are strong attraction. So strong attraction here. And the ions attracts the water just as strong. So this is strong attraction. It will dissolve. So it's kind of like when you want to dissolve in water, you will first need to break off these connections first. Because in order to dissolve in water, it means you want to make friends with water. And in order for you to make friends with water, you need to ask the water to stop making friends with each other first. So think of this as like an investment. So you, let's say, this is a strong attraction. So to break them, you may need to invest $1,000. But then in order to make friends with water, okay, you will form back a strong attraction. So this is like some kind of reward. You get back $1,000 in return. So if you spend $1,000 to break this connection, and you regain $1,000 from forming these new connections, you have nothing to lose in here, and so it is soluble. Okay, but then let's see what happens on the right hand side. In organic solvent, you see in here, so you will have to break this connection first. So these are strong attraction called ionic bonds. Yeah, and these are strong attractions that you will know later as hydrogen bond. Yeah, and on the right, can you draw what happens in an organic solvent? So this is an organic solvent. CHCl3. So I'll just draw CHCl3 this way. CHCl3. These are weak attraction. So weak attraction. And in an ionic compound, there is still strong attraction. Okay, so for ionic compound to dissolve, the ions will have to form weak attraction with CHCl3. Okay, like this. Yeah, I'll show you some math and then you will hopefully know what is going on next. Okay, so when these ions interact with CHCl3, they get back only weak attraction in return. Okay, so let's take a look at the math in here. Okay, so this is like cost, how much it costs you. Okay, so this is the cost. And this is the reward. Okay, so this is the reward here. If the reward can cover the cost, the process will happen, and then the substance will be soluble. But if the reward cannot cover the cost, okay, let's say you made a $1,000 investment, but you only get $1 in return, will you make this investment? No, nobody would do that, right? Same thing here. It is as if the ionic compound is trying to plan an investment. It will compare the cost and the reward. If the reward is just as strong as the cost, you see here, the cost is that you need to break strong attraction. The reward is that you form back some strong attraction. So you have nothing to lose here. You will want to make this investment. Well, at least you don't want to lose money when you make the investment, okay? So therefore we say this is soluble. So the cost and the reward are similar. So the reward can compensate for the cost. But on the right, the cost is that you need to break these strong attraction, but you only form back weak attraction in return. So these are weak attraction. So it's not able to cover the cost. So we say it will not be soluble. Now, I know this may sound a little bit complicated, but at the end of the day, you will just need to know that ionic structure are soluble in solvent and that they are insoluble in organic solvent. This explanation, you might not find it in such detail on the textbook. So if you can understand it, great. If you cannot, you just have to remember these two words again. So let me try to explain that to you again. Think of these strong attractions as like some $500 investment. Okay, both of them. And in return, you get back $1,000. Okay, so 500 plus 500 matches the reward, $1,000. Okay, so therefore they are solo. The reward can cover the cost. But on the right, you see these are weak attraction, meaning it costs you only $200 to break them. Yeah, but then it will cost you another $500 to break this strong attraction, and in return you only get back $200. Can you see that 200 plus 500 is larger than 200? Your original investment is larger than. Yeah, I don't want to make it all about money, but I think if we make it about money, then you will understand it a lot better than what you see on the textbook. What you see on the textbook, they focus only on the initial attraction. Yeah, they forgot to mention what happens in the ionic compound. Okay, so I think this will give you a better understanding of the solubility. Okay? Well, what about simple molecular substance? Okay, so when we look at simple molecular substance, and when we do revision, I want you to look at them. Yeah, you want to switch off your phone. Okay, so you have solubility of simple molecular substance. Any question you want to ask me, anything you want me to clarify first on this part? Okay? No? Okay, so we have solubility of simple molecular substance. So simple molecular substances. Can anyone give me an example of a simple molecular substance? So what is an example? We have discussed some examples of simple molecular substances like carbon dioxide, methane. Yeah, so these are simple molecular substances. So write down maybe carbon dioxide, in the wrong color. So carbon dioxide, HCl, so all these are simple molecular substances, okay, or maybe CH4. So what's so special about these molecules? Well, first of all, they are usually insoluble in aqueous solvent, but they are soluble in organic solvent. So it's like the reverse, you see. It's like the reverse of what we saw in ionic compound. While they are usually insoluble in aqueous solvent, they are, however, soluble in organic solvent. And let me try to explain that to you below, okay, using a very similar argument. So I'll copy this from on the left. So let's draw a beaker of water again. Water attracts each other by strong attractions. Yeah, let's say it is equivalent to a $500 investment. And then we have some CO2 molecules around. CO2 attracts each other with some weak attraction. So this is equivalent to a small amount investment. So let's make it $200. Yeah. When water and CO2 are to form interaction, they will reform some weak attraction. Okay, so you see in here, so this is H2O, this is H2O, this is H2O. These are again weak attractions. So that's equivalent to another $200. So if you are CO2, would you want to make this investment? You spent, your initial investment was $700, but you get only $200 in return. There's nothing in it for you, right? So therefore, it is a case of cost greater than reward here. So insoluble. That's how you understand it. What about the organic solvent? Why would they want to dissolve in organic solvent then? Well, that's because, let me use the weak attraction here again. So you have weak attraction of $200 worth, and then you have CO2. Okay, so that is equivalent to a like a $200 investment. Yeah, but okay, actually in here, yeah, I will have to say that at the end, the HCl3 and so the number are just for reference, okay? But because the resultant attraction is weak, it is similar to the attraction that are broken. Well, you have a case of cost similar to reward here. Okay, so cost similar to reward here. Well, this is a 2 times difference, 700 and 200, like more than a 2 times difference. And on the right, this is a smaller difference. So you have 200 plus 200, and this is like 400.
Right,
So, okay, sorry, let me just reconnect the screen first. Okay, so the numbers are just for your reference. Okay, the takeaway here is if you can form as strong an attraction as you break, it's soluble. If the attraction that you form is weaker than at least one of the starting attraction, you are not soluble. Okay, so let me simplify it this way. Write down the summary on top first. So when we dissolve something, we will need to break the solid attraction and the solvent attraction. Okay, so solid and solvent. So this attraction needs to be broken. And in exchange, the solid and the solvent will reform some attraction. Okay, like this. Right, so this is before and this is after. For something to dissolve, we need to first break this attraction. So break. Okay, so we need to first the attraction between solid and the attraction between solvent are broken. Okay, so between solvent so this is keyword broken. Then attraction between the solid and the solvent reforms. Okay, so you see here they are reforming. So you see while you break the attraction between the two solids, they no longer attract. You're now forming attraction between solid and solvent. So you have a band. Okay, so band attraction between solid and solvent reforms. Right, so if the green attraction is weaker than the red attraction, it will not dissolve. Okay, so if the green thing here, so if the attraction between solid and solvent is smaller, okay, then the attraction between the solid and the attraction between the solvents, then it will not dissolve. The substance will not dissolve. Okay? But if the attraction between the solid and the solvents matches, okay, the strength of either the attraction between solid or the attraction between solvent, the substance will dissolve. Okay, so the substance will dissolve. Right, so we have a case in here. Can you go back to this diagram here? Okay, you only have to remember these top two concepts in there. And take a look at these two diagrams again. Can you see that in here, when you look at giant ionic structures, you are reforming strong attraction in aqueous solvent, right? Yeah, that means it is just as strong as one of the two starting attraction. So this is why it is soluble. Okay, so it's soluble. But what about here? Can you see that this is weak? Yeah, this one is weaker than one of the starting attraction, okay, which is this case in here, you see. So therefore it will not dissolve. So this is rather complicated, okay? So if this is too much math for you, just remember that ionic structures and simple covalent, simple molecular substances, they have opposite solubility. They have opposite solubility. So one is soluble in water, but insoluble in organic solvent. The other is insoluble in organic solvent, but soluble, insoluble in aqueous solvent, but soluble in organic solvent. And then we have, what about giant covalent structure? Giant covalent structure is insoluble in both aqueous and organic solvent. Think about it. When you drop diamond into water, does it dissolve? No. When you drop diamond into oil, does it dissolve? Well, if it does, it wouldn't be worth so much, right? Yeah, if it dissolves so easily, right? So that way, you can remember that diamond, things that are giant covalent structure, they will not dissolve in both organic and aqueous solvent. Can you make this the third point on the next page? So we have the third category of substance here. So solubility of giant covalent structures, e.g. diamond. Okay, so diamond. Diamond will not dissolve in both aqueous and organic solvents. So we can, let me copy this over first. So it is actually insoluble in both. So I'll paste it in here. And this word I will need to change it also to insoluble. Because all the bonds are so strong, no amount of attraction can compensate for the attraction you break, okay, in these two solvents. So for this part, I will just write this as, so you can draw a diamond here. So I think by now you should be pretty good at drawing diamond, okay. So when you put water, okay, I put the diamond into water or in oil, okay, so they cannot break this attraction because these are too strong. What do we call these bonds? Strong covalent bonds, okay. There are just so many covalent bonds that you need to break. That will make your initial investment close to infinite. Your initial investment is like $10 billion, okay. So you know the reward cannot compensate for that. So there is a lot of because too many strong covalent bonds need to be broken. So covalent bonds need to be broken. It makes the initial cost very high, okay? So need to be broken for giant covalent structure to dissolve in either type of solvent. So giant covalent structures to dissolve in either type of solvent. So they will not be soluble in either of these. So let's do a summary. Okay, I know now you're overwhelmed by the facts, okay, that I present to you. So below we have a summary on solubility. All that you need to know is the table here. But I don't like students to just memorize facts. This is why I try to explain it to you. And I think with your ability you can understand it. But now that you understand it, you can just remember those points. So you have giant, so let's do a short review. Giant ionic structure, we have an example like NaCl. Then we have carbon dioxide. So this is a representative member of simple molecular substance. And finally, we have giant covalent structure with diamond being a representative substance. Okay, so let's take a look at the solubility. Okay, all in one place. On the side, giant covalent structure, e.g., diamond. Okay, so diamond. On the right, we look at their solubility in water. Okay, so solubility in aqueous, right, solvent, and then we have solubility in organic solvent. So with giant ionic structure, just remember table salt, because I'm sure you know what will happen to table salt when you drop it into water. They dissolve, right? They dissolve. Then try to add salt into oil tonight, and tell me back what will happen. It will not dissolve. Oil is an organic solvent. I really want you to try this so you remember. Okay? So put down soluble and insoluble. But I have to put a star here because it's just mostly soluble. There are some ionic compounds that are actually not soluble in water, and we'll turn to that in a much later chapter in acid and base. So usually, so I have to put a disclaimer here. So it's usually soluble. Salt is soluble. There are some other salts that are not soluble though. Okay, more on that later. Okay, I want to put a remark here. So later when you get to the acid and base chapter, you will know. Some salts are ionic compounds in chemistry. When you see the word salt, it doesn't always mean table salt. You know, sometimes at home you may use bath salt. When you go to the market, you may see rock salt. There are many types of salts in chemistry, not just table salt. The term salt means ionic compound in general in chemistry. Okay? So some salts or some ionic compounds are insoluble in water. More on that in the acid and base chapter, which you will learn in Form 5. Okay, so don't worry about them now, just remember general facts, most are soluble. Okay? Then we have simple molecular substances. They are the reverse, okay, the solubility. It is insoluble in water Yeah, so usually insoluble. Again, I need to put a disclaimer here. You know there are certain simple molecular substances that are quite soluble in water. Do you know what people use to sterilize swimming pool? Chlorine. Think about it. What is chlorine? Is chlorine a giant ionic structure or simple molecular substance? Simple molecular. Okay, so therefore usually. Okay, so put down a few exceptions, a few obvious exceptions. So some, there are always exceptions. This is what makes chemistry so difficult to study. Okay, so some are actually soluble. So just put down a few of these examples, including the HCl in your stomach. You know, if HCl is not soluble in water, why would you have acidic stomach juice? Okay, so HCl is hydrogen chloride. When it dissolves in water, it forms the acid in your stomach juice, hydrochloric acid. And then there is ammonia. Yeah, you know, ammonia is a very like a pungent smelling gas. Okay, so it is also quite soluble in water. Then we have sulfur dioxide. Okay, so sulfur dioxide. Yeah, that can dissolve in rain to form acid rain. Okay, so you can put down some application. So HCl dissolve in water to form stomach acid. Yeah, HCl. Okay, so it's gastric juice or gastric acid. Ammonia you can find in glass cleaner. So if you have mopped the window before with some kind of glass cleaner, okay, that's ammonia inside. And because it is soluble, you can turn it into a solution. So ammonia is in glass cleaner. If it is not soluble, you wouldn't be able to make a cleaner of any sort with it because it won't dissolve. But it does. It does dissolve. So that's why you can find it in glass cleaner, a solution. Then we have SO2. SO2 can dissolve in rain to form acid rain. Okay, maybe acid rain is not too serious a problem in Hong Kong because we don't have much industrial activities around. But in regions with a lot of industrial activities, there will be a very serious acid rain problem. Can dissolve in rain to form acid rain. Yeah, acid rain. Yeah, so just know these few exceptions for now. Okay, so they are usually insoluble, except these three. Yeah, and then we have giant covalent structure. Just remember diamond. Diamond will not be soluble in either. There are no exception here. Okay? Yeah, it must be insoluble in water, if not it would not be that expensive diamond. Yeah, it will also not dissolve in organic solvent. So you can think of aqueous solvent as water. Okay, as water. Think of organic solvent as something like oil. Okay, like oil. Yeah, and just ask yourself, what happens when you drop diamond in water and oil? It will not dissolve. What happens when you drop salt into water and oil? It will dissolve in water, but not in oil. Yeah, that way you can remember this. Now we have one more type of structure to cover before we wrap up this chapter and have a test. Yeah, so after today we'll have in the next lesson, we will arrange a test. Is it okay with that? Okay. Yeah, I will also go through some naming with you at the end of this class. Okay. So on the next page, I wanted to put down the last thing that we haven't yet covered. Giant metallic structure. Okay. So, any questions so far first? Any question? No. No. Okay. So now on a new page on a notebook, write down giant metallic structures. Okay, so giant metallic structure. So this structure is found in all metals. Yeah, so this structure can be found in all metals. Yeah, so in all metals. Mercury is no exception. Okay, so all metals. And the next chapter happens to be metal. Okay, so I make it the last thing we discussed. Okay. So the structure can be found in all metals. And in metal, there is what we call metallic bond. Okay, so we have metallic bond. So strong metallic bond. Makes sense. In ionic compound, we have ionic bond. In covalent substance, we have covalent bond. So now, when we look at giant metallic structure, of course, we have metallic bonds. So strong metallic bonds, can be seen. Okay, in metals. And this is how it works. Okay, so take sodium as an example. Okay, so take, what is the symbol of sodium? Na. Okay, so take Na as an example. If I tell you that the electron arrangement of Na is 11, can you tell me what is the electron arrangement? What is the electron arrangement of something with 11 electrons? 281. Okay, so write down electron arrangement is 281, which means is it stable or is it not stable currently? Not stable. Why is that? Yeah, the outermost shell is not full. Very good. So you have 281. So by looking at the last electron, the number in the last shell, you can tell that it is unhappy. It is unstable. So sodium will want to do something to make itself stable, and it's by stripping off the outermost layer. Okay, so like this. So this is sodium, you see, in its original form. You have 2, 8, 1. So sodium is unhappy with what it currently has. Okay, so it will strip away the outermost shell, and that extra electron will become delocalized. So you see that electron. So the outermost shell electron become delocalized. So this has two consequences. Number one, it is that it makes sodium more stable, as it now become, is it a 1 plus charge or 1 minus charge ion?
1 minus.
When you lose electron, you become more positive. Yes, you become a positively charged ion. At the same time, you get an electron. So we can write an equation describing what is happening here. So we have Na becoming Na plus an electron. So this is the electron. And you see the charge should be balanced on both sides. You have 0 charge on the left, but on the right you have 1 plus and 1 minus, which still add up to 0 overall charge, right? So therefore, you know something is wrong when you write Na minus here, because the charges don't count. This is one way to check your answer, okay? And tell me what have they become? This is sodium atom on the left, and on the right we have what we call a sodium cation. So this is an Na plus cation, and what we call a delocalized electron. And think about what happens when you have not just one Na, but many Nas around. Well, all the Na, they will do the same. So I want you to let's see if you can draw this. If you cannot, it's fine. So you have Na. Imagine that I have a block of Na metal. So at the beginning, all the Na inside this chunk of sodium metal, they are unhappy. Okay, so you see, so all these, this is a chunk of Na metal. Meaning, inside of this sodium metal, you will find a lot of sodium metals, sodium atoms that are protesting. Okay, they are unhappy right now. What they will do next is all of them will strip away an electron. Okay, so they will become something like this. And at the end, where will the electron go? Yeah, they will, all the electrons, they will become delocalized. Yeah, so you see each of the sodium, if they give up an electron, not only do they all become happy, there is also now a sea of delocalized electrons surrounding them. So can you put down before? And this is what happens after. Yeah, and we can simplify this diagram because this is so much to draw, right? So in the exam, you can simplify this diagram as just a bunch of positively charged ion. Yeah, you don't have to really show me the electron arrangement. That's not necessary. But you have to show me the localized electrons around them. Can you tell me where does metallic bond exist in this structure? You know what is a bond? What does a bond mean? A bond means attraction, right? Attraction between something positive and something negative. So can you tell me where do you see a bond in here? Between any pair of positive and negative charge things, right? Yeah, so these are metallic bonds. And do you notice something? Is that it seems like I'm drawing the orientation randomly, right?
Yes.
Yeah, that's because metallic bond is like that, okay? It doesn't require the electron to be in a certain location. As long as there is an electron around a certain positive ion, no matter where the electron goes, the metallic bond exists. It's kind of like I'm holding out a rope, and I ask you to hold onto the other end of the rope, and I'm swinging you around. It doesn't matter where you are at around it, a bond still exists, okay, between the two of us, okay? So can you put down what this is? This, we call it the strong metallic bond. Yeah, and it is non-directional, meaning it exists no matter where the electron is at. That's a very, very important feature. Yeah, so can you put down what we should put next to this purple arrow? So this is simplified as. Okay, so this is simplified as this. And in the exam, you really have to just draw me this. Okay, this structure. So put a star around this. Yeah. And when asked to, so this is the instruction in the question when they expect this diagram. Draw a diagram, okay, showing the structure of a metal, showing the structure of metal, and this is the solution. Okay, so if this is the question, then this will be the answer. Yeah, and we have to label. Yeah, so you see, even with Form 6, I just marked the pre-mock paper and date, even date. Don't read the question carefully. Okay, when I ask you to label it, it means you need to take out a ruler and label what these things are. Don't just draw a diagram and then move on to the next question. Okay, you label this as metal cations. Metals, can they form negative ion or can they only form positive ion? Can metal form negatively charged ions? No, why not? Where are they on the periodic table? Are they closer to the previous noble gas or to the next noble gas?
Previous.
The previous. Okay, let me show you. If you're unsure, you can always refer to the periodic table. Look at this periodic table first. This is where the metal resides, okay, on the left-hand side of the periodic table. Can you see that? Take Na and Mg as an example. Are these two metals closer to neon or are they closer to argon? Neon. That means metals are always closest to the previous, not the next noble gas. So therefore, they are better off losing electrons than to gain, right? Because think about it, if sodium wants to gain the stability of Ar, what does that mean? Sodium needs to gain 7 electrons. That's not great, because 7 electrons sounds a lot, right? But then sodium has another option. It can also strip away just 1 electron to become like neon. Yeah, so it can become stable. If you ask sodium, if you interview sodium and ask him, oh, what do you want to do now to become stable? If you are to choose between losing 1 or gaining 7, it will choose losing electron any day, right? So metals can only form cations. This is why I put metal cations, okay? And then we have, write down the localized C of the electron. So this represents a delocalized C of the electrons, okay? And you label this last thing as metallic bond. Okay, so this is metallic bond. Okay, right now we look at a very, very important feature next, and it is that metallic bond is non-directional. Okay, you need to understand the meaning of this term. So metallic bond is non-directional. Yeah, meaning the attraction exists everywhere. Yeah, so meaning this attraction is found everywhere, okay, inside the structure. So everywhere inside the metallic structure. So similarly, ionic bond is also non-directional because ionic bond is also found everywhere inside the structure, right? But what about covalent bond? I want you to think about covalent bond. Is covalent bond found everywhere inside the structure, or it's just found concentrated in a particular region? Concentrated in a particular region. So can you draw this comparison on the side? Ionic bond is also non-directional because it extends everywhere as well, just like a metallic bond. So can you draw a bunch of positive and negative charged ions? And from this diagram, I think you will agree that, well, yeah, just like metallic bond, ionic bond extends in all directions in the structure. So this is why it's also non-directional. But covalent bond, not so much. Covalent bond is directional. So covalent bond is, however, directional. So what does that mean? When you look at a molecule of hydrogen, so this is H, you will find only covalent bond here. Do you find it outside this molecule? Can you find a covalent bond outside this molecule? No. So because you can only find the covalent bond right between the two hydrogen atoms, but nowhere else. It's not found everywhere, okay? Only when something is found everywhere do you say that it's non-directional. Take a look at this diagram again. In metallic bond, in metallic structure, you see metallic bond everywhere, so non-directional. In giant ionic structure, you see ionic bonds everywhere, so it's non-directional. But in covalent bond, you only see covalent bonds in between the atoms. You don't see it outside these atoms. Okay, not here, not in this space. Yeah, not in this space. So therefore, it is directional. Okay, so put some annotation here. So covalent bond is, sorry. Let me try this again. Right, so covalent bond is found here. Okay, only. Yeah, and here, and here. But it is not found here, here, and here. Yeah, so but it is not found here. In other words, this is not found everywhere, therefore making it directional. Right, so that's a comparison between like a metallic bond, ionic bond, and covalent bond. Any question about the bond first? Yeah, so covalent bond is found in these positions only, but not in other positions. Okay, so it's directional. Now we will look at some properties unique to metal. Okay, you see metal is a very amazing type of material because first of all, it's conductive. Okay, we have a lot of uses of something conductive. For example, they are used in electronic devices. So next up, we look at the property. Yeah, after you finish copying these, okay, we will look at the properties of metals. Okay, or the properties of giant metallic structure, and understand why metal will want to form metallic bond. Because by forming metallic bond, it solves two problems at the same time. Number one, it makes itself stable. So I forgot to draw a happy face here. So can you write down 2,8? So now that it has stripped away the outermost shell, it is now happy. It is now stable. Don't say happy in exam. You can only write stable in exam. Okay, so this is unstable on the left, and this is now stable. So this is why it wants to form metallic bond, because by forming metallic bond, it makes itself stable. Okay? Right. On the opposite side, we will look at the other metals. Okay? So strength of metallic bond. So strength of metallic bond. Okay. Right, sodium, magnesium, and aluminum, when we compare them, yeah, we found that aluminum is the metal with the highest melting point. And why is that? Okay, so when you look at Na, Mg, and Al, so Mg has 12 electrons, Na has 11 electrons, Al has 13 electrons. So that means when they are to form like a metallic bond, what would they want to do? Well, how many electrons do they want to lose? So for sodium, how many electrons does it want to lose? Sodium, just one. But what about magnesium? Is losing one enough for magnesium to bring it to stability? No. It will need to lose 2. And for aluminum, it will need to lose 3. So therefore, by stripping away a different number of outermost shell electrons, they will get to 2,8. Yeah, but it is at the cost losing different number of electrons. So can you put down for sodium, it will have to lose 1 to bring it to stability. And magnesium lose 2, aluminum lose 3. So the consequence of this is that sodium will become Na plus ion. So can you draw this? So in Na we have Na plus and 1 electron. In magnesium there will be Mg2 plus and 2 electrons. And in aluminium there will be Al3 plus and 3 electrons. Okay, so can you draw 1 electron each here? And you have 2 electrons next to each of those ions, and yeah, just 1 more here. Okay, and can you tell me which of these metals will have the strongest metallic bond? Is it in Na, Mg, or Al?
Al.
Al, yeah. So can you put down why? This is Na, this is Mg, this is Al. Each of these we call it Na plus cation, and these Mg2 plus cation. You can see that the charge is slowly increasing from 1 plus a cation to 2 plus and finally 3 plus charge a cation. And you know what? In physics, we know that the bigger the charge of two charged substance, the stronger the attraction between them. So this is why, can you draw some dotted line here to show that the metallic bond is not really that strong in sodium? Yeah, it is strong, but compared to magnesium, it's not very strong. Yeah, and then you see, what about in aluminum? Aluminum has the strongest metallic bond of all 3, period. Okay, so can you draw like a triangle here and show the strength of metallic bond? Yeah, so strength of metallic bond increases with the charge of metal ion. So next time when, in exam they ask you why would aluminum have the highest melting point of all 3 metals? You know they are all metals and they all have metallic bond. Why will some metals with stronger metallic bond than the others? Well, that's because of this extremely important point. Strength of metallic bond increases with the charge of the metal ion. The bigger the charge, the stronger the metallic bond. Is that clear? And how do we know the charge? We look at what it takes to bring them to stability, to bring them to a stable electronic configuration. Okay? So you know these are unstable on the left. And by losing a different number of electrons, they become cations, okay, and they become stable. Right, so that's the strength of metallic bond. We will now look at the properties of metal, okay, and if you have seen any metals before, then I'm sure most of these properties you are already aware of. So can you put them down? So properties. First of all, metals, they have pretty high melting and boiling point. This is why they exist as a solid at over a very wide range of temperature, making them very useful. Yeah, you know the probes we send to space. You know those probes in the spacecraft, okay? That they are made mostly of metals, okay? Yeah, and if they would melt at low temperature, it wouldn't be a suitable material, okay, for use in spacecraft or things, because we are sometimes sending these probes to very hot areas, like whatever, to Mercury, to the planet Mercury, or to near the sun maybe. So we need some very high melting point substance. So here we look at the properties of giant metallic structures, starting with number 1, high melting and boiling point. This is thanks to the, and also you can take out the worksheet, so we can fill out this table a long time. Yeah, so we are at the last column, this last column, that will complete your understanding. In terms of melting and boiling point, they are pretty high. Yeah, so high melting and boiling point because metallic bond is strong. Okay, so metallic bond is strong, and that it exists between cations and a delocalized sea of electron. Okay, so and the localized C of the electron, remember the label diagram we drew? These are the localized C of the electron. Okay, if you like, you can draw more than one line here, okay, to indicate that what you're referring to these C of the electron. Okay, I like to think of it as like these are a bunch of like people, like metal cations. Okay, they are bathing in some electrons. Okay, the electrons surround them. Okay, so they are surrounded by electrons. So the localized C of electrons. So number one, we know they have high melting and boiling point. So there's only one metal that has a low enough boiling point, a melting point for it to exist as a liquid at room temperature. That's mercury. Okay, so like exception, write down. Mercury, okay, has low enough a melting point for it to exist as a liquid. Okay, for it to exist as liquid. So rumor has it that the Chinese emperor, like I don't know what you call him, like Chen Qi Emperor Qi. Don't know him. A rumor has it that he surrounded his tomb because he killed a lot of people during his ruling. So he, in order to prevent people from taking revenge on him by raiding his tomb, rumor has it that nobody has found his tomb just yet. Rumor has it that he surrounds his tomb with full of mercury. Okay, just to kill anyone who tried to raid his tomb. And he installed a lot of contraption. Okay, so if you know about Chinese history, you can look it up. Okay, Emperor Qin. Okay, QIN. Right. So we have high melting point. Mercury is toxic. Okay, and that is a liquid. And then we have number two. Well, electrical conductivity. Everybody must know about this. All metals are excellent electrical conductor. Because do you remember what electrical conductivity depends on? One of two things. You either need mobile ions or you need a delocalized C of electrons. If you can provide one of these, you are a conductor. So electrical conductor, you can write down this is because metals all have again delocalized C of electrons. Okay, and let me tell you what happens when you complete the circuit. Remember this device we use to check the conductivity of something? Yeah. But sadly, we can't see the flow of electrons, but we can picture what it is like when we complete the circuit. So can you draw this diagram 2 times? Yeah. Before we close the switch, and after we close the switch, okay, you see this will happen. At the beginning, the light bulb does not light up. Yeah. Well, because you haven't completed the circuit. But as soon as you close the circuit, the light bulb lights up. And this thing in here, I placed between the crocodile clip, is actually a piece of metal. Can you draw out what happens inside the metal before I close and after I close the circuit? Before I close the circuit, the electrons are wandering aimlessly. Okay, so electrons is just like they have no goal at this moment. They are just wandering around aimlessly like that. Now let me just check if you have learned science correctly. What do you call this longer and the shorter arm? Which one is positive, which one is negative?
Positive is the longer one.
Yes, positive is the longer one. Now, can you predict what will happen when I close the switch? You know, if this is positive, it will make this end also positive, right? Yeah, if this is positive, this end, if this clip is also made positive. And if this is negative, that other clip at that other position will also be negative. Now, if you are the electron inside the metal, in which direction should you move now inside the metal? Will you move all the way to the left? Or will you move all the way to the right, which makes more sense? You are electrons. Electrons are negatively charged. And negatively charged electrons, they should all move towards left. Yes. Okay, so can you draw the diagram here? Yeah, but we cannot do experiment to see this, unfortunately, okay? However, we imagine that the electrons, they will all be moving in one direction as soon as you close or complete the circuit. Yeah, so can you put this down? Before the circuit is closed, Yeah, electrons moves randomly. So electron moves randomly. But after the circuit is completed, okay, electron moves in one direction only. Okay, and then this way electrons can leave the circuit and just keep on moving around the circuit. Okay, like that. So that's the second property. And then we have hardness and strength. Okay, so hardness and strength. For metal, we use two adjectives to describe them, which I think you have heard of before. It's malleable and ductile. Okay, so hardness or strength. Metals are pretty strong, but they can deform easily. Okay, so we use these terms to describe metal. So metals are hard, but when a stress is applied, it deforms easily. So when a stress is applied, if you have a metallic ruler, I think you might have tried bending it around before. You know, it doesn't just crack, it will just deform, right? But if you do this to a plastic ruler, you know the plastic ruler, it will not remain in that deformed state, it will just crack, right? Or it will just glance back. So this is how metal respond to stress. Metals are hard, but when the stress is applied, they deform, okay, easily. We can also explain this this way. So imagine that I have a piece of metal. Okay, so this is like a metallic ruler. So this is a metallic ruler. What happens when I bend it? Okay, so you see when I bend it, why doesn't it break easily? Well, I mean, if you try hard enough, you can break a metallic ruler if you flex it too much. Okay, but when you just bend it around slightly, it doesn't break. That's because when you look inside, you see these are the metal cations again. Remember the non-directional nature of metallic bond? The non-directional nature of metallic bond means even when you bend the ruler around, can metallic bond still exist or will it be broken already? It will still exist. So this is why metals, they are unusual in that when you bend them around, they don't just break. Okay, they will deform first before they finally give in and break. Okay, so there's some tolerance, you see. So you can write down why do they deform easily. This is because layers of atoms or cations, can slide past one another freely. Slide past one another freely. So therefore, and that metallic bond is non-directional. So it doesn't break easily. Instead it deforms. It changes shape. So a metallic bond, okay, is the keyword non-directional. Okay, so you see it was here, and it is still here. Okay, so it exists everywhere inside the structure. It won't be because the layers of atoms have shifted slightly that the metallic bond is broken. So can you put down two words on the next page because I ran out of space here. Malleable and ductile. They are slightly different in meaning. So describing metals, we use these two terms. Malleable and ductile. Like I think I told you before, if you have eaten those desserts decorated with gold foils, you know what malleable means. Because gold is a metal. Even if you have a very, very tiny piece of gold, when you hammer it, you can turn it into very, very thin foil. Okay? So this hammerability, if that's even a word, we call this malleability. Okay, so malleability is the ability to turn into thin sheets. Okay, so malleability, write down the word. You need to know how to spell it. Okay, you can also use malleable when you just describe the metal. So malleability is the ability to form thin sheets. Okay, and then there's another word, ductility. When you say that metal is ductile, it means when you're pulling it from both sides. So imagine there to be two invisible hands here. Okay, so two invisible hands here. When you are pulling it, so pull from both sides. you can turn metal into long and thin wire. Okay, so this thing right here is thin sheets, okay, of metal. And here you have a long and thin wire. So that's when we use the term ductility. So ductility is the ability to be turned into long and thin wire. I mean, if you try to do this to wood, it will break. The wood cannot be deformed into very long, thin shapes, okay, or thin sheets. But metal has both of these properties, thanks to the non-directional nature of metallic bond. You see, the non-directional nature of metallic bond allows the structure to deform like to a great extent without breaking. So this is why thin foil is possible. Long and thin wire is also possible. So to be turned into thin wires. So metal has both properties. So can you put down the word hard but malleable and ductile for in this box? Hardness and strength for diametallic structure. Okay. So this will be on the test. Okay. So metals have both of these properties. Okay? And finally, to wrap this all up, what about the solubility in organic solvent and in water? Well, technically, metal is insoluble in both solvents. Okay, so metal is insoluble in both solvents. So solubility in solvent. When you drop a paperclip in water, it did not dissolve. When you drop paperclip into oil, it did not dissolve. Okay, so that's because metal should be insoluble in both. But as you will see in the next chapter, sometimes you see metal dissolving in water, and that's not because it dissolved, it's because it reacted. Okay, it reacts. So you can put down generally, I must put a huge disclaimer here. So they are insoluble, okay, in both aqueous and organic solvent. So aqueous and organic solvent. Just remember that. When you put an iron nail, so this is iron nail. When you put it in water, it does not dissolve. When you put it in oil, it also does not dissolve. But some metals seems like they will dissolve in water. Okay. That's because let me finish this last sentence. Some metals, especially the reactive ones, so some reactive metals, remember that video I showed you where the guy throws some sodium into water, it boom, explodes, right? And if you look inside, the metal is gone because it may look like it has dissolved, but it actually reacted. So some metal reacts with instead of dissolving in water. Okay? Right. So we will have a test on metals. Okay, for book 1B. Okay, book 1B. So last time we had a test on 1A, platinum. So now we'll next lesson. Okay, the next lesson. Next time we have lesson, we'll arrange a test on microscopic water. Okay, right? Yeah. So please refer to the notes.
Flow. Have a try.
Turn you. Go somewhere and listen to the Go spread. Go spread. Go somewhere and you want to